Hey everyone, and welcome. If you're a developer, you've probably dealt with HTTPS, but today we're going to pull back the curtain and really demystify it. We'll break down the core crypto concepts you need to know to build truly secure apps. So let's just dive right in.
You see that little lock icon in your browser every single day, right? We all have this gut feeling that it means things are secure. But what is it really doing under the hood? What promises is it actually making? That's exactly what we're going to unpack today.
So, before we get into the nitty-gritty of how HTTPS works, we first have to agree on the goal. What does secure communication even mean? It really boils down to three very specific guarantees. Okay, think about logging into your bank. First, you want confidentiality. You don't want someone at the same coffee shop snooping on your Wi-Fi and grabbing your password. Simple enough. Next, you need integrity. You want to be sure that when you transfer $100, a hacker can't secretly change that to $1,000 mid-flight. And finally, and this is a big one, you absolutely need authentication. You have to be 100% certain you're talking to your actual bank's website and not some clever fake. These three pillars, confidentiality, integrity, and authentication, are what HTTPS is built to deliver.
So to achieve those three guarantees, we need some tools. And the first, most basic tool in our cryptographic toolbox is something called Symmetric Encryption.
The core idea here is, incredibly straightforward. One key does everything. You use the exact same secret key to scramble the data, and then you use that very same key to unscramble it on the other side. It's that simple. The best way to picture this is with a physical lockbox. Imagine you and a friend both have identical keys. You can lock a message inside the box, send it over, and they can use their identical key to open it. Now, this method has a huge advantage. It's incredibly fast, and that's fantastic for encrypting a lot of data. But it's got one massive, glaring weakness. How did you get that key to your friend securely in the first place?
So when you see this in code, the flow is always the same. First, you generate a single secret key. You use that key to encrypt your message. Then, on the other end, the receiver uses that exact same key to decrypt it. One key, two jobs, locking and unlocking.
And that right there brings us to the million-dollar question. If you and a server you've never talked to before need to communicate, how on earth can you agree on a secret key without some eavesdropper on the internet just grabbing a copy as it flies by? This is the fundamental problem that symmetric encryption just can't solve on its own.
Well, the solution to that key sharing problem is a really beautiful and elegant concept called asymmetric encryption. And this is where the real magic starts to happen.
Now, instead of one key, you generate a pair of keys that are mathematically linked together. You get a public key and a private key. The public key is for locking things. You can and should share it with the entire world. But the private key, that's for unlocking, and you guard that with your life. You keep it completely secret.
The classic analogy here is a mailbox with a mail slot. Anyone in the world can walk up and drop a letter into that public slot, but only the person with the private key, the owner, can actually open the box and read the letters inside. See how that works? So the process is totally different. You start by generating a pair of keys. You give your public key to anyone who asks for it. They can then use that public key to encrypt a message. And the magic is that message can now only be decrypted by your corresponding private key, which you, of course, kept secret. Okay, so let's put them side by side. Symmetric encryption has one key, it's really fast, and it's perfect for encrypting the actual bulk data of your conversation. Asymmetric encryption, on the other hand, has two keys, it's much, much slower, but its whole job is to solve that original problem, securely exchanging another key. Now, asymmetric encryption has another amazing trick up its sleeve. It's not just for taking secrets. You can also use it to prove your identity, using something called a digital signature.
A digital signature is all about proving authenticity and integrity. And what you do is you basically reverse the process we just talked about. You use your private key to create a unique signature for a piece of data. Then anybody with your public key can verify that signature, and since you're the only one with the private key, it's mathematical proof that the message came from you and that it hasn't been tampered with.
Okay, so now we have all the pieces on the board. We've got symmetric encryption for speed, asymmetric encryption for that crucial key exchange, and digital signatures to prove who's who. So let's see how HTTPS brilliantly combines all of these to secure our traffic on the web.
Here's the genius of it. HTTPS is a hybrid system.
It doesn't choose one method over the other. It uses the slow, heavy-duty asymmetric encryption for one, and only one, very specific job: to safely agree on a brand new, temporary symmetric key. As soon as that's done, it switches over to the super-fast symmetric encryption for the rest of the conversation. It really is the best of both worlds.
But wait a second. How do you know the public key you just got actually belongs to your bank? That's a huge question, and the answer is a digital certificate. The best way to think of this is like a website's passport or its driver's license. It's a data file that contains the website's public key, its domain name, and most importantly, a digital signature from a trusted third party called a certificate authority, or a CA.
This whole initial setup dance is called the TLS Handshake, and it goes something like this. Step 1. Your browser says hello to the server. Step 2. The server responds by sending back its digital certificate, which, remember, has its public key inside. Your browser checks that the certificate is legit. Then, step 3, your browser creates a brand new symmetric key, encrypts it using the server's public key, and sends it back. Finally, in step 4, the server uses its private key to decrypt that message, and boom! Both sides now share the same secret symmetric key, and the rest of the conversation can happen quickly and securely.
Okay, so that's the theory. It's pretty cool stuff. But what does this actually mean for you as a developer in your day-to-day work? Let's boil this all down into a practical summary.
So here's your high-level cheat sheet. When you need to encrypt a ton of data and do it fast, you're looking at symmetric algorithms like AES 256. When you need to securely exchange a key or prove your identity with a digital signature, that's a job for asymmetric algorithms like RSA. A digital certificate, that's what binds a key to a domain name. And the TLS handshake is that hybrid process that puts it all into action to set up a secure session.
And please, here are some absolute non-negotiable best practices. First, never, ever, ever hard-code keys or credentials in your source code. Use a proper secrets manager for that. Second, always use HTTPS everywhere, even on localhost in development, so you don't get any nasty surprises in production. Also, make sure your servers are configured to enforce modern protocols like TLS 1.2 and especially 1.3. And finally, whatever you do, never ever tell your code to disable certificate verification. That's basically like leaving the front door of your house wide open.
So we've seen how HTTPS brilliantly establishes a secure channel for communication over an insecure network like the internet. But that just pushes the problem one step further, doesn't it? The security of this entire system hinges on keeping those private keys secret, which leaves one final critical question for you to think about. How do you truly secure and manage those all-important keys in a real, live production environment? And that, my friends, is the next step on your security journey.